Hey, Toby here. Can you hear me?
Yep.
Perfect. Thank you so much for joining. Let me just share my screen and get started. Hopefully this will work. Is everyone able to see the presentation?
We see it in editing mode.
Perfect. I have not been using WebEx for a very long time, so I'll see if it works. And now it's hopefully in presentation mode.
Exactly, perfect.
Perfect. Thank you so much. So yes, as Edmund said, my name is Tobias. I'm a machine learning engineer at SigOpt, a company acquired by Intel almost 2 years ago. What I'll be talking about today is intelligent experimentation and a little bit about what we do at SigOpt, and then give you an overview of some of the technology that we have been developing for the past seven-ish years. If there are any questions, please interrupt me, put them in the chat, or save them to the end. But yeah, thank you so much for joining, and hopefully you'll all learn something. Excuse me. There we go. So what we've been doing for the past 7 years is we've tried to empower teams to really build the best possible models, whether it is machine learning, high performance computing, or even things such as manufacturing. A lot of the people that we've been working with are, the OpenAIs of the world, where it's really about sort of designing new experiments that creates novel approaches to, things such as text generation. But we've also been working with the company, like with the two Sigmas of the world, where it's all about building the best models at scale. Two Sigma is a algorithmic trading firm, and when you're in that space, it's really a zero-sum game, because if your competition builds better models than yourself, you'll lose money. But if you build the best models, you'll win. It's simple as that. And then the final group that we've been working a lot with are the universities of the world, the academic institutions, where it's all about sort of developing new insights, developing new approaches to modeling, etc., etc. That's just to give you some idea about the folks that we've been working with. And here's just a snapshot of some of the folks. Some of them are household names. A lot of them you've probably never heard of. But these are some of our customers, collaborators, etc., etc. So what do we mean when we say intelligent experimentation? So personally, I like to think about it in the terms of what it's not, because if you think about experimentation is very much, or what it's trying to do is provide insights into cause and effect by demonstrating what outcomes occur when a particular component is manipulated. So, when you go out, set up an experiment, it's really all about, trying to change things and see how that affects the outcome. Trying to develop new drugs, new methodologies, etc., etc. But it's really this sort of trial and error approach where, okay, if we manipulate this one thing, what happens? And then go through a long list of things that we can change. When thinking about intelligent experimentations, really it's about it's more about making recommendations. So really it's all about sort of designing a system and then go out to explore that system in order to find the optimal solution, the optimal outcome for this system. So the difference is we're not just going with trial and error, Here, we're trying to find the optimal solution or the optimal set of solutions, because as you can imagine, for most problems, no single solution exists. If you think about, let's say, machine learning, it makes sense to come up with a model that has the highest accuracy. But in the context of putting this into production, most likely you have multiple other things that define success for this machine, like this particular model. Similar if you're developing, let's say, batteries, solar panels, or something completely different. You most likely have a long list of competing objectives. So there, as you're defining these experiments, it's really about being able to pinpoint what maximizes the value for me, what maximizes the value for my business. And really, that's what we've been investigating over the years. That how do you do that in an easy, scalable way? What I'll be talking about today is in the context of machine learning. I hope that's something that most folks can relate to. But all the things that I'm talking about today is easily transferable to things such as manufacturing, high performance computing, or drug discovery, et cetera, et cetera. Any questions? I will take silence as a no. So really, this idea of intelligent experimentation has sort of three components to it. One, which is design. You want to be able to design a system. The second thing is this idea of exploration. When you have designed your system, how do you go about exploring it? Then finally, when you have the confidence in your system, how do you go about optimizing it? That being said, it is this cycle where as you go through different types of models, different types of manufacturing processes, you will always end up going back to this idea of designing an experiment based on the insights that you have obtained. So for most problems, unfortunately, there do not exist one single solution, but it's this iterative process, and hopefully we're able to get better and better over time. And again, what we're trying to provide is software that enhances this sort of iterative process, allows you to define experiments, store, track, and then finally optimize, and then use all of that information for the next iteration of your design process. So let's talk a little bit about it in the context of machine learning. Just excuse me. So again, all of the things here is transferable to things such as manufacturing or high performance computing, or pretty much anything that has this notion of finding optimums, of finding better solutions. Hopefully you are able to see those in the context of what I'll be talking about now. But let's talk about machine learning, because really there it's all about finding the optimal solution for your modeling problem. The optimal solution for a modeling problem, unfortunately, is not always the optimal model when it comes to things such as testing these models. But I'll talk about that in a second. But really, the idea of design when building out machine learning models, that's all of the things that most folks are already doing today. It's sourcing the data, version, it's cleaning the data, feature engineering, augmentation, all of that, really that's part of designing the system. I think that people tend to forget that, and just think of it as, oh, this is what I need to do in order to do my job properly. I need to clean my data set. I need to do a little bit of feature engineering, et cetera, et cetera. But really, there is a tremendous amount of value in doing that, and being able to do it efficiently saves you time, but it also gives you the opportunity to learn, okay, how does this decision that I'm making now, early in my development life cycle, how will that affect sort of the end state of this this model application that I'm developing. Then secondly, you know, things such as choosing not just the framework, but also choosing like what type of model to use. Like it makes sense for like early on in a lot of projects to just go with something really, really simple. Excuse me. It makes sense to go with something really, really simple. You take a simple library and just get off the ground. But as things evolve, as things becomes more and more complex, how does one keep track of all of the things that has been done? How does one make the most informed decision on what to do next? All of that's part of the design process as well. And then finally, as we're building out machine learning models, deep learning models, the first step there is, define the math that will lead to the best possible model. So one part of that is also figuring out like how do we sort of define success from a mathematical point of view, because as I mentioned earlier, it's not necessarily the optimal solution for the model that is the optimal solution for the problem that we're trying to solve. However, in order to go towards the optimal solution for our problem, we need to define, okay, what does success look like? And again, that's also part of this whole design process. Any questions? I will take silence as a no. So, in order to get all of these decisions right, the solution honestly is pretty straightforward. It's all about sort of, being able to try out things efficiently and being able to track how the decisions that you're making affects the overall outcome. So one of the things that is part of the technology that we've designed is, it's an easy way to track all of the modeling that is going on, all of the experimentation that you're doing, without having to change anything in the workflow that you're having today. So that's really just the step one is, track everything and make sure that you can go back in time and, use all of that information to make informed decisions. So nothing real fancy here. And one thing I should have mentioned is that kind of the software that we're providing, it's a SaaS solution. So the second that you start to track things and monitor, okay, how are different things doing, all of that goes straight into a dashboard that then becomes then becomes your system of record. But again, nothing real fancy here. But hopefully, as I go through the example later on, it becomes more clear what's going on. Then the second thing is this idea of exploration, exploring. Because if you think about most of the machine learning libraries that folks are using today, all of them has this idea of model.fit. Like you create an object that is your model, and you pipe through some data, and you get a model out on the other end. Like that's really the methodology behind most machine learning libraries, I would say. What goes into this model, of course, changes. Some of the simple libraries, these are all pre-built APIs. As things, increases in complexity, you have the ability to, stack together layers, using the Keras API, and that really affects how this model look. But the second you have built this model, it's just all about piping some data through, being able to monitor the results. That being said, the second that you're going from having just one model, having a model, to having a really a use case, that's where you need to think about, okay, what are really the metrics that mean something for me? What are the metrics that define success for me as a developer, a machine learning engineer, or something else? And really, the first step here is this idea of training metrics. Some people will argue that your training metrics is the exact same thing as your loss function. No, it's a fair statement, and it's true in some cases. The problem is, however, that we as human beings are not particularly good at understanding things that lives in a log space. And really, if you're just blindly looking at your loss functions, it makes sense to try to minimize it, but there is only so much you can learn from it. That's why it makes sense to figure out, okay, what are really the metrics that what are the metrics that mean something for my use case? Really the place in which I'm going to use this model that I'm developing. Like, how do I justify that this model is really training towards something that is meaningful? Then, also, as you can imagine, a lot of these machine learning models, in order for them to train, they're taking these, incremental steps ahead of time, or into time. And in order to really understand what is going on, we need to be able to track that progression through time as well. Similarly, or I shouldn't say similarly, I said unfortunately, if we just start to look at only the training metrics, as you can imagine, we will get to a pretty good point fairly quickly, because if there's one thing that machine learning models are really, really good at, it's overfitting. So we need to be able to generalize or we need to be able to make sure that our models can generalize. And that's where something like a validation metric comes into play. That's where you as the developer, you split your data sets into two, and you say, okay, I don't care about what happens on my training metrics. Really, all I care about is my validation metrics, because again, this is data unseen to the model. So I assume that my model will perform better. Like I assume that if I do well on this data, it'll also do well on real world. It can be true, it can also not be true, but it's a reasonable thing to do. And it's a fairly simple and straightforward way to search for models that is able to generalize. Now, really the more important things, at least in my opinion, is sort of being able to guardrail your model, your metrics, because again, taking your training metric and your validation metric and say, okay, this is accuracy as an example. That talks a lot about the performance of this model. However, it talks very little about how your model is doing in the context of your actual use cases. So one example could be self-driving cars. You have a car, it has a bunch of cameras, and you have some model that is trying to interpret the world around this car. In that case, some of the things you need to make sure is true is that you are able to detect objects, pedestrians, trees, whatever you may have, really, really quickly. Because again, maybe you have the best model in the world, but if it takes multiple seconds for you to detect anything, chances are the second that you realize, oh, this is pedestrian, you already hit that pedestrian. That's not the best case scenario for a self-driving car. Similarly, if you have cameras in all directions, you need to be able to really interpret all of those images simultaneously. Otherwise you'll only be able to see, okay, what happens on one side of the car, or in front of the car but not in the back. Similarly, you don't have the luxury of a serverless system. You have a fixed amount of computation resources on this car. So you need to be able to make sure that this best model that you're producing is able to fit within the car. Similar, you have a finite set of power. You need to make sure that this model you're producing is not taking up all of the power in the car. Then maybe you need to interpret, like being able to interpret results, etc. Or maybe there is some very specific needs. All of this is very much tied to the use case, but really, when you're looking at real world use cases, you need to be able to really put all of the modeling that you're doing into a much larger context that represents this specific use case. That's also one of the things that we're focusing on a lot, and hopefully this becomes clear when I show you a short demo in just a second. Any questions? Unfortunately, there is one thing that is even more challenging than looking at validation metrics, training metrics, guardrail metrics, etc. And that is what happens when I put my model into production. And I think for a lot of the work going on within machine learning, like being able to solve the problem of sort of production metrics. It has a lot of different flavors, but I think for a lot of people, that's really that's really the holy grail, because that is what that is what tells you about what is happening the second that the machine learning application that you have developed wanders into the real world. Because again, you can get feedback out in the real world, things such as did the customer purchase or not, and did we make a profit or not. But really, those are not the same metrics as the ones we used for validation. So being able to think about that is extremely important and challenging, but it's a fun thing to think about. I'd say. Let's talk more about it in a second. But really, it's it's all about being able to, like, all of these things. It's really all about being able to design the system, and then as you're wandering through the system, through different configurations of that system, like how does one interpret results? That's really what it's all about. Of of course you can layer in sort of some level of intelligence to it, but it's really all about interpreting the results in the most meaningful way. And again, if things becomes very high dimensional, it's really hard for us to interpret, and that's where layering in some sort of automation, or some way of compressing results into something that can be interpreted makes sense. Makes a lot of sense. I'll show that in a second. So all of the things that I just talked about, in my opinion, those are all kind of necessary evils to some extent. That's where you're able to again design the system, track everything that is going on, interpret results, etc. Like where we started out as a company is in the space of optimization. That's historically where we've been focused. Then we have layered in things such as sort of tracking and tracing capabilities that make the life of our users easier, but it's really centered around this idea of optimization, and how do we make optimization more sort of both better, more accessible, and really that's all we do, honestly. Here is kind of an interaction diagram of how optimization looks, because one thing we have learned is people are, don't know if you can imagine, but people are very sensitive about the data, about the models. So there are, no way in which our users will allow us to touch the data, to touch the models. So we've developed this system where all of the things that you see on on the left, that's your environment. That's where you have your data, you have your models, and you have your sort of evaluation framework, validation framework, or whatever you want to call it. Then on the right side, that's all SigOpt. This is SigOpt backend. That is the optimization engine that you have the ability to access. Fairly simple, but really then the interaction flow is at least in the context of machine learning, that's where you define the experiment through this idea of hyperparameters. You have your usual suspects that sits within the model, but you also have a long list of parameters that can be tied directly to, say, the use case, the infrastructure that you're using. Define all of that, ship that information to SigOpt, then I'll provide you with some configuration of your parameters. You'll then put that into your model, train your model, test your model, and then return this long list of metrics back and get a new configuration. And again, in the context of machine learning, this is pretty straightforward. This is, hyperparameter optimization. This is what most folks are doing today already. We just developed algorithms that is easy to use, well performing, very generally. Again, if you have a very specific problem, of developed optimization algorithms for that specific problem over a long period of time, they should most likely work better than sort of the general algorithms that we have designed. However, as you wander into things such as manufacturing, things becomes a lot more both expensive and complex. So if you were to imagine that the left-hand side is not just your laptop where you're training some machine learning model. All of that is real, like everything on there on the left. That's a production facility where you are developing glass for some solar panels. That's something we've been working on for a while. That's really, really, really expensive to produce one sheet of glass, and you have a long list of metrics that represent success. So is rainwater able to run down the sheet of glass? Does things stick to the glass? Is there any type of reflection, etc., etc.? All of these things. So that's where you will design the system, having all of these metrics. And again, then it's not just like one metric, like the accuracy that you're sending back to SigOpt. It's really like a long list of how well this sheet of glass did across a bunch of different basically tests. But the problem is also, it's super expensive. So you need to be able to come up with, not come up with, because we did that, like use optimization algorithms that are extremely sample efficient and that you can control in terms of, in terms of how much time or how many resources can I afford to allocate, and then making sure that you get the optimal solution within the time really that you have allocated. That's where something like SigOpt comes into play, and then you can use it for hyperparameter optimization as well. It's the exact same methodology. Then we've layered in a lot of things around multi-metric optimization. Again, as I talked about with both the self-driving cars and the glass, there are there are a lot of metrics that really represent success, and you need to be able to optimize across, as many as you need ultimately. But the problem is, if you have two metrics, you don't have just a single point that represents success. What you have is this Pareto frontier. Chances are you'll always lose on one metric and also win on the other one. Think of the example as size, like number of parameters versus the accuracy of machine learning model. Chances are the models with the most parameters most likely actually not parameters, let's say inference time. The biggest model is the one that has the highest accuracy, but most likely also the lowest inference time, and vice versa. So as you're optimizing multiple metrics, it's really all about finding this efficient frontier that you as the expert can choose from. Then, as I mentioned, if you've been developing your own algorithms, chances are they're much better at your specific problems than whatever we can come up with. But we have spent a lot of time developing very scalable infrastructure to do math, to do optimization. You can take advantage of that fairly easily. So you don't have to worry about it. And then finally, a lot of other things within the realm of optimization may be finding multiple solutions, being able to add constraints in both the parameter space and the metric space, failures, low fidelity search, transferring between different experiments, all of these things that makes up optimization. All of that can be accessed within the same sort of user interface, so that you can take advantage of those algorithms. Any questions? Otherwise, we have a few minutes left, and I'll show a very quick demo. And it's all about sort of design, explore, and optimize. Really, that's the key, and being able to sort of track everything, and learn from a things that has been going on. Just show a 2-minute demo, 3-minute demo. You can sign up for free for the SigOpt platform on sigopt.com/signup, and you can just start to use it. All of these resources are there as well, so it's really easy to get off the ground. But just want to give you an idea about what's going on. Really, from a user perspective, everything runs through a client library. So it's pip install SigOpt. You import the libraries as you normally would. Like all of that is straightforward. I need an identifier that's just for my own purposes. And really, the way in which you connect to the SigOpt backend from your model environment is through this idea of an API token. So the second that you sign up for SigOpt, you get access to the UI. Sign in. This is what you see in here. You have your own unique API token. That's all you really need to connect to the backend. You plug that in. You load your data. You do your feature engineering, and then you start to prepare for modeling. And really, those are all of the things that you're doing today. Nothing has changed in your workflow whatsoever. Where things start to change is here. Like here, I'm developing a few helper functions that for basically just plotting purposes, because I can all of that will go and live on the dashboard. So these are all nice helper functions, such that when I do my modeling, everything is centralized in one place. So of that, I have my long list of metrics. Again, that's things that I'm doing today, is like already doing. I create a SigOpt project. That's the first place where one is going to really interact with the SigOpt backend. I'll show what that looks like in a second. And then you create your model. Again, this is hopefully what most folks are doing today. The things you change is you'll log information about data sets, models. On top of that, you define, okay, what are my my parameters in this model, my default parameters. I build my model based on these parameters. I train my model, I test my model, and I report all of the metrics back to the SigOpt dashboard to together with my images, and all of that. See if all of that goes to live on the web dashboard. I can go in and see the runs that I created, have a laundry list of my metrics, information about model types, my default parameters, and then I have all of these visualizations that I just created, lives nicely on the dashboard. All of that is the sort of the tracking and tracing capabilities, this necessary evil, because where we go into optimization, and then this is how all of that happens automatically the second that you train your model, like execute that function you just created. But this is where things becomes interesting. This is where you are defining the experiment, saying, okay, these are my parameters. These are the spans, the types. And then similarly, I define my metric space. In this situation, I'm looking at my accuracy, but because I'm looking, it's for this particular use case, it's categorizing tumors as either malignant or benign. I'm also adding in these guardrail metrics saying, hey, I only care about the highest accuracy if I can satisfy this constraint on my malignant, similar on the benign, and then just track my my rock area, and then like this, go through 20 iterations. Then you kick that off, and then the second you do that, the all of the results from this what we call the experiment goes to live on the dashboard. You can track the progression over time. You can go and analyze the results even deeper, saying, okay, what of my metrics had an impact? You can also see, okay, what points did actually satisfy my constraints, etc., etc. And I think now my time is up. But again, you can go to sigopt.com/signup, start using it, and hopefully by doing so you'll get a much clearer understanding of what's going on. Any questions?